has questions. I think we're through 3-4 as of today, right? Mackenzie? Yeah, can you give me an approximate page number there? No idea? That's okay. I got it. I gotcha. 205. Okay, and you said 43?
Yes.
Sure. All right, so if I look at 43, initially this looks a little confusing because I have a whole lot of letters floating around in here. But if you look at the function, I can tell that x is really the only variable. Everything else I can treat as a constant, even though it's a letter. The g of x tells me that the x is the actual variable. Anything else in there is a constant. So I can kind of ignore everything that's a non, or I can treat everything other than the x's as a constant. So this is a chain rule, right? I have some inside stuff and some outside stuff. So just applying the chain rule, the derivative of the outer is I'm going to have rho times the insides to the rho minus 1. And then I'll have the derivative of the inside, where that piece I'm going to just think about as 2r times the exponential a to the rx. Is that okay, Mackenzie? That is also a chain rule problem. So the derivative of an exponential is just the exponential times the natural log of the base. And then the derivative of the exponent is just going to be r. And then when I differentiate the n, that just gives me 0, since it's a constant. And now I could try to clean this up a little bit or whatever, but I'm not super interested in that. I'm pretty happy with what I have here. Is that okay, Mackenzie?
Yeah.
Are you sure?
Yeah.
Yeah, no problems. Like, again, take a moment and process. If you're not sure, we can follow up or whatever.
So can you repeat the ln a part?
Yeah, so the derivative of a to the x is a to the x ln a. So when I did this, if we think about this as a composition, say like h of x is x to the rho, and then hi of x would be the inner stuffs. So g prime would have been h prime of I of x times the derivative of I of x. And I of x, we see that, well, this piece is a chain rule part there. So maybe I say j of x is a to the x, and then k of x would be like rx. So when I do that, I have, instead of, if I'm doing the derivative of I of x, or of I of x, I would have 2r, and then the derivative of j of k of x, times the derivative of k of x, and then I'd still have plus the derivative of n, which would just be 0. So if I was filling this all in, the derivative of h would be rho times x to the rho minus 1. And then the derivative of j is a to the x ln a. And then the derivative of k of x is just r. Does that feel okay? And again, like, until you get really comfortable, I think it's often quite helpful to like write out the derivative symbolically and then just do the little derivatives, because it's less to kind of keep a hold of in your mind. Because there's a lot of stuff rattling around there. To just go straight from question to answer is sometimes a little tough. But if you work through like the derivative steps symbolically, and then just like, okay, I just need to take a bunch of little derivatives and do a couple function compositions, and like what I'm doing is already written down for me, so it's a little bit easier to kind of keep track of things. I think that's often quite helpful, especially early on when you're getting the hang of things. Does that feel better, Mackenzie? Okay. Mia? Same section? Sure.
So like I have a question, like on the test, does the book, like when you look at the answers, it like simplifies it down a lot?
Yes.
So on the test, like you don't really care for that?
On a test setting, if I'm looking for a specific amount of simplification, the way I'd format the question is show that the derivative of this is equal to this. Where I'll give you the answer, and your job is now like algebraically to show me step by step how you've gone from taking the derivative to this simplified answer that I'm looking for. Otherwise, I would tell you that you're done when the calculus is done. Okay? So I think that that's probably the fairest way to do that kind of thing. If I'm looking for a specific amount of simplification, I'll tell you, like, this is the answer you need to get to, and now it's your responsibility to show me how you got there. Where the emphasis there is going to be on, like, the work shown in between on your intermediary steps. Since you have the final answer, you can't just like, oh, it equals this, done. Well, no. But I think that that's probably feels fair, right?
Yeah.
Okay. Okay. So 61 says if f of x equals the composition of f and g, where these are a bunch of specific values, find f of 5. Okay. Well, that's going to be the derivative of f of g of 5 times the derivative of g at 5. Everybody happy with that? Just basically applied the chain rule definition, right? Okay. We're told that g of 5 is -2. And we're told that g prime of 5 is 6. And then I know that f prime of negative 2 is 4. So I think I should get 24. Does that match the answer in the back, Leon? Yeah, I mean, okay, good. Yeah, I can't imagine they wanted you to, I think they just gave you extra information so it got confusing, right? So they gave you the f prime of negative 2 and f prime of 5, just so that it wasn't like, if you made a mistake of making the chain rule or like doing the compositions, like you had the piece that you would have needed to make your mistake, which is not an uncommon thing, right? Particularly on like a standardized test, they'll often give you more than you need. Victoria?
How did you get like that first equation?
That's just the chain rule, right? So I'm given a function that's a composition, right? So I just took the derivative of f, right? The chain rule
And like,
specifically would be this, right? And then I just plugged the 5 in. I just did it all in one step. Is that okay?
yeah, no, I understand.
Okay. Cool. Mackenzie? 65, same section? Sure. All right. Says f and g are functions whose graphs are shown below. Let u of x equal f of g of x, v of x equal g of f of x, and w of x equal g of x. Find each derivative if it exists, and if not, explain why. Okay? So u prime of 1 would be f, derivative of f of g of x, g of 1, times the derivative of g at 1. Everybody cool there? Okay. Well, g is the blue line, so at 1, g is equal to 3. Everybody's okay with that? Now, the derivative of g at 1 is going to be the slope of the tangent line on that section. Since it's a straight line, the slope for all of that section is going to be the same. The derivative for every point on that section is going to be the same. And I can just calculate it by using the slope formula. So I have here the point, let's see, 3, 4, 5, 6. So this is like 0, 6. And that was 1, 3. So the slope there is -3. And then f of 3, or f prime of 3, 1, 2, 3, is going to be the tangent line on that section. Well, again, that section, or that point, is just on this straight line, so the slope on every part of that straight line is the same. So I just need the slope for that straight line. So let's see here. That is the point 2, 4 right there. And then that is the point 2, 3, 4, 5, 6, 3. So yeah, it looks like the would be -1/4. So when I do that, I get +3/4. Does that feel okay with everybody? So parts B and C are going to be the exact same idea. So V prime of x would be G prime, or I'm sorry, V prime of 1 would be, yeah. Yeah, so -3 times -1/4 gave me positive 3/4.
No, I mean for the row above, like F1 and 3. Are you supposed to
No, the -1/4 is f prime of 3.
So it's just the slope that we have.
Yeah, you're just using slopes. Since they're straight lines, the derivatives are just going to be the slopes at that point, which is just the same as the slope of the line,
Right.
because it's a straight line. If these were curved, you couldn't do this problem.
Okay.
Had to have straight lines in order to do this, because the slope on that section of the straight line is the same for every point on that straight line. That's how we're going to calculate the derivatives.
Right.
It's just by calculating the slopes on those straight line
I
sections.
see what you mean. It's curved.
Exact. Well, the slope is
don't have
different
like a-
every
yeah,
time.
you don't
Yeah,
have
there's
slope
no way to,
constant.
right. You could approximate it, but like that's a pain in the, you know.
Approximately, we just put the closest
You'd
numbers on the side.
pick 2 points and like do the same tricks we did way back in section like 2-1 or whatever,
Remember that.
which is like, you know, kind of a pain in the tuchus. All right, so if I do this one, f prime of 1 is here. So that looks like that's 2. Or I'm sorry, f of 1 is 2. And f prime of 1 is going to be the slope on that section. So that goes from 0, 0 up to 2, 4. So the slope there was 2. And then G prime of 2 is going to be the slope at that point. Uh-oh. What's the derivative at that point? Doesn't exist. Why? It's a corner. I shouldn't say it's. Is that looking good?
Yep.
The last one, W prime of 1 is G prime of G of 1 times G prime of 1. Well, G of 1 we already found was 3. G prime of 1 we already found was -3. And then G prime of 3 would be the slope at that point there.
Which is -1/4, probably.
Nope. Which is going from 2, 0 to 6, 1, 2, 3. Well, maybe we'll stop here. We'll go from 1, 2, 3 to.
Wow.
So we go from 2, 0 to 3, 2. No, that can't be right. That's
right?
that. Yeah, it should be 4, 2. So 2, 3, 4, 5, 2. So that's going to be 2/3. In hindsight, seeing that I had to do 3 of these, what would have been smarter would have been just to figure out the slope for each of those sections in advance. So I could have just done these derivatives really quickly, because the biggest hassle is going back and calculating these derivatives. Now seeing that I'm going to need to do like 6 derivatives for f and g, maybe it would have just been easier for me to have calculated the slope on each of those sections. So if I'm doing a derivative, it's just like, yeah, there's the value, and just boom, boom, boom. Might have been less confusing for me to jump back and forth. But oh well. Mackenzie, you happy with that? Okay. Again, like, this is a nice problem because you're forced to use like multiple representations of what a derivative means. So you're forced to like use graphical representations and algebraic representation and like use a graph to calculate a derivative. And this is absolutely something I could see being like an AP multiple choice kind of question. This feels very nice. Like conceptual kind of question where it's like, can you really use one of these derivative rules in conjunction with figuring out a derivative from a graph? Anybody else? Okay. I want to give you guys a little heads up that probably Friday feels like a good day to maybe do a homework quiz. So I would say if you're up through 3-4, you should feel in fine shape. You should be able to use the derivative rules that we've covered up through then. So like be able to do the derivative of trig functions and polynomials and things that could be written in the polynomial form, like square roots or whatever, exponentials, and be able to use the product, quotient, and chain rules. Maybe in combination in some cases.
It's like an AP multiple choice kind of thing.
I'm going to hand you a sheet of paper with a couple of questions on it, and you're going to show your work and hand it back to me, and I'm going to just check them.
And are we going to have a test next week? Or is it just, that's the one day?
Well, we got to see how far we get today with 3-5. Well, here's the thing, guys. If there's a particularly bad day and Mr. Kulik's initial plan would be to schedule the test for that day, you can just tell me, and we'll just continue doing stuff and take the test later. You know me. I've done this before. This is not an unreasonable request to make.
We just like do a test after coming back. Do like a
Yeah.
test after coming back from the like that.
Oh, from the weird week next week?
Yeah.
Yeah,
So
that,
I give 2 tests.
yeah, I don't have any problem with not doing a test next week, and we'll just do it when we get back, right? Like, just talk to me. Like, you know me. I don't care when we take tests,
I appreciate you.
right? Like,
Other teachers kind of not like that.
well, here's the thing. We'll just keep going, right? Like, we're further away from the material, but if that helps you, I'm fine with it. It doesn't hurt me at all. We're going to just keep moving. The test doesn't get any longer, any bigger. We're just going to cover material after, that doesn't appear on the test, but it's fine. All right. So what we're going to be talking about today is something called implicit differentiation. Implicit differentiation is going to be done we use implicit differentiation when there's not a clear independent and dependent variable established. So, Mr. Kulik, what would that look like? Well, what if you have something that looks like this? There's no clear independent and dependent variable established, right? So maybe we ask for the derivative of y with respect to x. Everybody's okay so far? Okay. So just like we've done before, I'm just going to take the derivative, and we're going to do it to both sides of our equation. So far, so good. Now, the derivative on the left-hand side just kind of distributes, right? Everybody happy with that? Okay. Now, what's the derivative of x squared with respect to x? 2x. Okay. And what's the derivative of y squared with respect to x? 2y. Close. You're missing something, though. So let me just do a quick example over here on the side. So if I want to say find dy dx here, we would do the same thing, right? We take the derivative of both sides. So this is an aside, not related directly to what we're doing. What does the derivative of y become? Becomes 1 times dy dx, right? Well, when I ask for the derivative of this, you'd write something like y prime equals 2x, right? Y prime is the same thing as dy dx, right? It doesn't just, the y just doesn't disappear. Well, the y part, but it turns into a derivative, like a dy dx. Whenever you differentiate with respect to something that's not the variable you're differentiating, it creates one of these differentials. You could even think about one being created when we do x, but what is it, that differential? It's dx over dx, which is 1. It's nothing, right? So we don't really ever write that, even though it's kind of there. Mackenzie? Nope, go ahead.
So I'm a little confused on what the difference between dy over dx is and d over dx.
Okay, so dy over dx is describing the rate of change in y divided by the rate and change of x. Or I shouldn't say rate, it's just like the change in y divided by the change in x. Dx over dx would be the change in x divided by the change in x, which is like just 1, right? Dy dx is like the slope, like change in y over change in x. Does that?
So then when it's put in a problem, do you ever use dy over dx in a problem, or like d over dx is just
the d over dx is the operation. That's just saying we're taking the derivative with respect to x.
Okay.
Dy over dx is like the derivative.
Okay.
So like that's like your answer. That's what we're looking to get by itself. The d over dx is like the operation of taking a derivative.
Got it.
Does that make sense? Okay. Yeah, that's a great question, notationally. Like, what's the difference between d dx and dy dx? One is the operation, and the other is like the notation for the answer. Okay. So if I take this then, this is what I am looking for, is the dy dx. So now I'm just going to algebraically get the dy dx by itself. How would I do that? I subtract 2x from both sides, and then divide by 2y. And that'll just give me negative x over y. Is everybody okay with that? Let's do another. Call this just a here. B, let's say we have x cubed plus y cubed equals 6xy. Well, and we want to find dy dx. So again, we'll just start by taking the derivative of both sides. The derivative of x cubed with respect to x is 3x squared. And the derivative of y cubed with respect to x is
3y squared times the derivative of y with the derivative of x.
Yeah. 3y squared dy dx. And then how do I do dy dx of 6xy?
That should be 6.
Nope. 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 This is a product rule.
Yay.
So you'd have 6 times x times the derivative of y plus y times the derivative of x. Because we have 2 variables multiplied together. That's going to be a product rule. Oh, Mr. Kulik. Great googly moogly.
That was cool.
I wasn't expecting that.
Good job.
So the derivative of y just becomes 1 dy dx. And the derivative of x just becomes 1. Then we'll distribute the 6 through, because I notice what has happened here is I have dy dx in more than one location, right? So what I'm going to do is I'm going to move the dy dx's so that they're on the same side, and the terms that don't have a dy dx, I'm going to move to the other side. So I'm going to subtract over the 6x dy dx, and then I'll subtract over the 3x squared, so that all my dy dx's are on the same side. I'm then going to factor that off. And then divide by the 3y squared minus 6x to get the dy dx by itself.
Awesome.
So notice, as we're doing this, no new derivative technique has been introduced here, right? We've just added this idea that like, oh, if you differentiate a variable with respect to some other variable, it creates that differential, like the dy dx or whatever. But it doesn't really change what we're doing. Let's do, yes.
Can you factor out 3?
Sure, you could reduce this, absolutely. So Elvis is saying that we could factor a 3 out of both the numerator and denominator to reduce that. Yes, absolutely could do that. 100%. Good observation. How about this guy? Sine of x plus y equals y squared cosine x. So again, we're looking to find dy dx, so we'll take the derivative of both sides. So to take the derivative with respect to x of sine x plus y, what do we need to use? How do we do that?
Oh, chain rule.
Chain rule. Okay, what's the outer function? Sine. So the derivative of sine is cosine, and the inside stays the same. Then we have multiplied by the derivative of the inside. So the derivative of x plus y becomes
1 plus 1.
1 plus 1 times dy dx. And if you didn't put the 1 times the dy dx, that's fine, because it's,
Just 1.
yeah,
So you could just do 1 plus like
dy dx.
dy dx.
Yeah, like that would be fine. In fact, that's what I would have written. But I put the 1 there so that you can see what happened or whatever. Okay, now how do I take the derivative of y squared times cosine x? Product rule, yeah. So we're going to have y squared times the derivative with respect to x of cosine x plus cosine x times the derivative with respect to x of y squared.
So basically anything you do to y is going to result in dy or dx.
If you're taking a derivative and there's a y involved, you're going to get a dy dx tumbling out of that guy. Okay. The derivative of cosine is, well, I should say the derivative with respect to x of cosine x is negative sine x. I said we should be specific here since we have more than one variable in the problem. And the derivative of y squared is 2y dy dx. Exactly. All right. So, all right, I guess we got to distribute through that cosine xy. Or cosine x plus y, excuse me. And then just like before, I'm going to move everything with the dy dx onto one side and everything without the dy dx's to the other. Maybe I should say each term instead of thing. Let's be specific. Everybody okay there? Factor off the dy dx. And then divide by the cosine xy minus 2y cos x. And if I were to simplify this, what's the only simplifying I would consider? Dividing a negative through, right? You can, instead of having 3 negative signs, you could just have one negative sign. Yeah, that would be what I would, the only simplifying that I would see possible here. Oops, that's supposed to be plus. But I wouldn't, on my paper, I certainly wouldn't penalize you for not doing that. Like, that's whatever. Okay. Another example. What letter am I on? D or something? Call this a new example. So let's say we have x to the fourth plus y to the fourth equals 16. It's a pretty terrible looking 6, Mr. Kulik. And we want to know what the second derivative of y is equal to. So I'm just going to use the other notation here, since just for flavor. You could do this writing dy dx or d dx's. But since they're using the prime notation, I'm going to use the prime notation when I do that. Is that okay? It's not right or wrong. I'm just doing it with a different notation because, I don't know, it's good to see both ways, or both ways to write it. So we'll take the derivative of both sides. The derivative of x to the fourth becomes 4x cubed. The derivative of y to the fourth becomes 4y cubed times y prime. And the derivative of 16 is 0. What's the y prime doing? It's the same as dy dx, right? Just a different notation, so it just looks a little different. Either notation is fine to use, right? I'm just doing this one so you can see what it looks like the other way. I kind of prefer the first version, but there's nothing wrong with this, and sometimes this becomes considerably more compact, which is nice. Okay. So if I get the y prime by itself, again, I get negative x cubed over y cubed. I'm just going to shortcut through some algebra there, but it was the same algebra we saw when we did x squared plus y squared equals 4, right? Okay. Now I have the choice. I can either do the derivative of both sides here, or I can do it here. It doesn't really matter. But look at the two choices. In one, in the green box, I'd have to use a product property. In the yellow box, I have to use a quotient property and then sort out the quotients. I'd probably prefer using the green box to do this, because I'd rather not deal with the fractions if I don't really have to. I need the second derivative, yeah. So I would probably use that. And you might be questioning me, Mr. Kulik, why did you bother to get the yellow box there? I'll show you in a second because I'm going to use it still. All right, so the derivative of 4x cubed is going to become 12x squared. Everybody agree? The derivative of 4y cubed times y prime is a product rule. There's a product between the y cubed and the y prime. Everybody okay with the notation that I've used there? The derivative of the first derivative is just the second derivative. The derivative of 4y cubed becomes 12y squared times y prime. Does that feel okay with everybody? Now, if I do y prime times y prime, does that give me y double prime? No. It would give you y prime squared, but not y double prime. Everybody's good with that? Okay. So, all I'm going to do now is get the y prime by itself. So I would have subtracted the 12x squared over and subtracted the y prime. Let's do this right. 12y squared, y prime squared, and then divided by 4y cubed. And now, I'm going to make my substitution here. Because when we write our derivative, we shouldn't have another derivative inside that problem. So that'll reduce down then. X cubed over y cubed squared is going to kill the negative sign by squaring it. And I'll have x to the sixth over y to the sixth. But I'm multiplying that by a y squared. So this is really going to turn into like 12x to the sixth over y to the fourth. Everybody okay there? And then I'm going to clear the fraction inside of a fraction by multiplying the top and bottom by y to the fourth. Now, Mr. Kulik sees some sneaky stuff that he can pull here to simplify this mega more. Watch this. So I notice in the numerator I have a greatest common factor of negative 12 x squared. Sure, what's up, Victoria?
When you see like the x cubed divided by y cubed to the second,
Yes,
why is it y 4?
because I reduced the y squared in the numerator with the y sixth in the denominator.
Oh, so it's y 6. Okay.
I just did that all in one step. Is that okay?
Yeah.
Okay. And for sure, if you miss something like that, I think I said it what I was doing as I was doing it. But if you missed that, like, certainly ask about it. It looks suspicious, like that looks like a mistake Mr. Kulik made, and it's just because he didn't include every single detail. There's one more very sneaky piece of simplification here. Do you ever recognize that? That's 16. Why is that 16? Go back to the very original problem. X squared plus y squared is equal to 16. Oof! Mr. Kulik, are you serious? That is I would not have come up with that. Well, again, 15 years being a math teacher, like all but dissertation PhD math student. Like, this is what you get. So if we reduce that, I get negative 48 x squared over y to the 7th. And that's as good as you can get it. That's kind of as hard as I would make something like this, right? Is asking to do a second derivative is kind of an implicit is kind of as hard as they get, where you have to back substitute in at some point the first derivative. But they're all kind of the same. The algebra gets kind of sucky at the end, though. Okay. We also, in this section, add in some more derivative rules. Which I'm just going to drop in here, and we're going to prove one of them. So these are derivatives for the inverse trig functions. We're going to prove one of them.
Okay.
And the proofs are pretty similar for each of them, so I'm just going to do one of them as an exemplar.
Gotcha.
Yep. I'll drop this into the stuff to memorize page here eventually also.
That's self-memorizing. It's very much expanding. Over the course of the year.
Well, again, like a lot of it is just Mr. Kulik's not being very discerning. He's just grabbing every red box in the textbook as he's going through. Like, some of the stuff is just like, yeah, I don't really need to memorize that. I know it, kind of thing. Like, but I'm just putting it all in one place for you to do your own weeding as you see fit. It just seems like it's going to be easier for you if you're making like a Quizlet or something. Just kind of like just scan through and be like, yep, that's a derivative formula. Those are the things that I like absolutely have to have memorized. The rest is conceptual stuff that I don't need to like. I just need to understand. I don't necessarily have to have like, I need this verbatim. Or like the derivative of cosine, you have to know is negative sine. Like, you're just like, it's something-ish like that. No, it's like you have to know that.
Yeah.
Like these things, you have to know these things. I know. All right. So let's do one. So we're going to prove this one.
You need to know all 6.
Mm-hmm. I know.
No.
I know. Again, like, make a Quizlet, make some flashcards, just spend like 5 minutes every other day or something, and it won't be an issue. But like, Unfortunately, it is what it is. Like they expect you to know them. They pop up on the AP exams. You got to be able to do these. There's no other way other than memorizing them. You're not going to have enough time to rederive them. Even if that was a realistic option for you, just time-wise, you just have to have it memorized. I'm sorry. All right. So the derivative, or I'm sorry, we're going to be taking the derivative of sine inverse, right? So I'm going to start with the function y equals sine inverse of x. That's equivalent to sine of y equals x, provided that you're working on this domain. Why am I doing that? Why did I include that extra restriction to the domain? Because it wouldn't have been a function without it, right? Sine of y with respect to x is going to look like that. By restricting the domain, you just get like, that thing. Like just that little piece of it, which is now a function, right? So that's all that's doing there. All right, so let's do the derivative then. So the derivative of sine, or derivative with respect to x of sine y, is going to be cosine y dy dx equals 1. Everybody's good with that? So dy dx is going to equal 1 over cosine y Now, we have to think about it for a minute. Oops, that was a big mistake, Mr. Kulik. That was supposed to be a y there. Y being, the angles being between negative pi over 2 and positive pi over 2. What quadrants are we working with there? Quadrants 4 and 1. What can we say about cosine in quadrants 4 and 1? It's greater than or equal to 0. If you think back to your unit circle, in quadrants 1 and 4, the x-coordinate is always positive, or I should say non-negative. Cosine is the x-coordinate from the unit circle. All those values for cosine should be non-negative.
This is a proof, right?
Mm-hmm. Correct. So, why do I need that? Well, remember that sine squared plus cosine squared is equal to 1. I can then say cosine is equal to plus or minus the square root 1 minus sine squared. But because of this, what can I do? Drop the negative. And remind me again, sine of y squared then is going to be the same as x squared. And there's my finish. And that's going to do it for section 3.5. So section 3.5, again, you're going to see these new inverse trig function derivatives pop up here and there. But realistically, we haven't added any new rules. We've just talked about this implicit situation, but we're still just using like product quotient chain rules in combination with the other little derivative shortcuts we've learned. How are we doing?
So we're going to use these the cosine inverses and 1.5 examples.
There'll be some problems where those derivative rules will be used in this homework.
It's
Yes.
just kind of like substitute.
Basically, yes. Yep. All right. I want to also start 3.6. We'll just start it. And here's the deal. You guys ready? Okay, if we do this, start this today, we'll just do the homework quiz on Friday and take some questions, and that'll be it. Okay? Is that a good trade?
Yeah. Wait, then for the test, you're gonna give us like a day where we can like walk through some of the questions here.
Yeah, for sure. I mean, I'm still probably going to need another some more time in section 3.6. I just want to start it today so that tomorrow I don't feel like I'm rushed to try to start something. Mia?
I don't know if this was right, but what's in the questions?
They're just going to be like, do the derivative of this thing. That's it. Up through chain rule.
Okay.
Yep. That's 3.4. So it's nothing conceptual, nothing like the tangent line of this thing is at 0, you know, like there's no words other than like take the derivative and like some instructions about how I want you to, like what I want you to do as far as like the non-simplifying that's okay. But that's it. So it's just going to be all symbolic, like just symbol pushing. We should feel pretty comfortable with these types of problems.
Is it 3.4?
Yeah. Okay. So there's two new derivative rules in 3.6. The first is the derivative of any logarithm is going to be 1 over x times the natural log of b. And then specifically then, the net derivative of the natural log is just going to be 1 over x times the natural log of e, which is just 1. So it's going to be 1 over x. We're going to prove that first one. Oops. So if we just say we have the equation y equals log base b of x, remember our definition of a logarithm from Algebra 2? I'd say then that x is equal to b to the y. If I take the derivative with respect to x of both sides, I get 1 equals b to the y natural log of b times dy dx. And now if I solve, I'm going to have 1 over b to the y natural log b equals dy dx. And notice that b to the y is equal to x. So just to run through a couple of examples. Let's say I have y equals the natural log of x cubed plus 1. What do we see here? Chain rule, right? What's the outside? The natural log. What's the inside? X cubed plus 1. So dy dx should equal f prime of g of x times g prime of x. F prime of x is 1 over x. G prime of x is equal to 3x squared. So what do we have here then? 1 over x cubed plus 1 times 3x squared, or just 3x squared over x cubed plus 1.
So you use the chain rule.
Yep. That's it. Chain rule in this new derivative of a natural log. Is that okay? It's so reassuring.
Wait, can you just zoom in?
Mm-hmm. Yeah, can I write the next one?
Yeah.
Okay. Okay, what if we have log of, oops, should probably say y equals log of 2 plus sine x. What do you guys see? Hopefully another chain rule. So the derivative of the log of x is 1 over x, natural log of 10. And the derivative of g is going to be cosine x. So I'm going to have 1 over 2x plus sine x times the natural log of 10 times cosine x. So just multiply some fractions and good enough. Oh no, Mr. Kulik. What do you guys see here? Two chains and a quotient. That's what you probably see, right? You know what Mr. Kulik sees? I see 3 easy chain rules. I see 3 easy chain rules. Mm-hmm.
So, you know how like you do like the little equations like f of x, f prime of x, g of x, g prime.
Mm-hmm.
Like there obviously there's gonna be like you said like there's gonna be more. There's gonna be like h of x, h prime of x.
If there's more than one chain, if you have more like one chain inside of a chain,
Right.
this when I do this, it's gonna be 3 separate chain rules, no links.
Okay. Which but when there are 3 chains,
Mm-hmm.
is there like an equation for that? So I can just plug it in.
Yeah.
I know that's probably like 3.4, 5.
Yeah, it would be like f prime of g of h of x times g prime of h of x times h prime of x. I think we did some examples in there where we did that. But here, what's the trick, Mr. Kulik? Because I don't see any way not doing a quotient rule. Well, it's because you don't remember your properties of logarithms.
This is 1 over the. No, that's wrong.
And you're like, Mr. Kulik, do I really need these? I'm like, it's going to be a massive time saver to have that. So my first order of business is to rewrite this as an expansion of logs, right? Do you remember the order that we want to do these properties in? Quotient, product, power when we're expanding a logarithm. So applying the quotient property, I'd have this. Remember that a square root is the same as an exponent of 1/2. Everybody's okay there? Now I'm going to do my differentiating because look at how easy this is going to be. I have just 2 little easy chain rules. dy dx equals 1 over x plus 1 times the derivative of x plus 1, which is just 1, minus 1/2 times 1 over x minus 2 times the derivative of x minus 2, which is just 1. Done. I'd wager if you tried to do this as like a linked chain rule and a quotient rule, like you'd still be writing. Meanwhile, Mr. Kulik finished that in like 2 lines. Very easy. These guys are your friends. Now, the natural question here should be, wait a minute, Mr. Kulik. Could I just do this for any problem? Yeah. Yeah, we can. So, for example, had we had y equals x plus 1 over square root x minus 2, what you could do is you could do like the natural log of both sides. So the derivative of y is going to be 1 over y dy dx. And then this, we already did. Right? And then we just multiply both sides by y. And I'm done. What? This process here that we just used is called logarithmic differentiation. And what it's going to allow us to do is not have to do like a big complicated derivative where you have like chain rules and product rules and quotient rules and more chain rules and it's all like mucked together. If it's like in the right form, you can just do the natural log of both sides, break it all apart, and just do a bunch of single link chain rules. Victoria.
Can you scroll up a little? When you put like, you know how it's square root of x minus 2?
Yeah.
And you just put the 1/2 and then the log of x minus 2. What happens to like the product for like the -1?
So the square root is the same thing as the exponent 1/2. So I use the power property to move the 1/2 to the coefficient.
What happens to the negative? Like if the product is like nx n minus 1. What happens to 1/2 minus 1?
I don't need to do it because I didn't do the product rule there. I didn't use the power. I used the power rule for logarithms. I used this property, not a derivative. Not a derivative. I just used the property of logarithms, which like way simplifies it.